Hello, welcome to another reading session of an article titled Controlled Phase Change of GST on SOI for Photonic Neuromorphic Application. And authors are Rakshita Kalega, Rupali Shekhawat, Uday Bhatke, Ramesh Karupannam, and Shankar Kumar Shelvaraja. So, abstract goes like this. We demonstrate controlled phase tuning of thermal evaporated germanium antimony telluride. In short, GST, germanium antimony telluride, integrated silicon ring resonator. The controlled cyclic allows access to multi-states, resulting in multi-photonic states for the potential neuromorphic application. We present and correlate electrical and photonic phase transition of ring integrated GST. So in this, we demonstrate controlled phase tuning. So what is this? It is a controlled phase tuning of thermal evaporated germanium antimony telluride integrated silicon ring resonator. So here we have a micro ring resonator, and GST means germanium antimony telluride has been used. The control cyclic allows access to multi states. So some things are there, multi states in multi-photonic states. So there are more photonic states for the potential neuromorphic application. So let us see introduction. Silicon photonics offers a versatile platform for various applications. The ability to confine and manipulate light propagation has resulted in disruptive technology in communication and sensing. So here we need to know what is this disruptive technology. One of the long-standing expectations is computing at the speed of light. Photonic integrated circuits offer an opportunity to explore the feasibility of an optical computing scheme. Current computing technology is based on von Neumann architecture, which relies on discrete functional units, processing unit, memory, and communication bus. Photonic integrated circuits are already considered the next generation interconnect technology to improve the communication bus, to improve bandwidth bottleneck or von Neumann bottleneck. So here this von Neumann bottleneck. An ultimate solution would be to combine the process and memory unit. Combine the process and memory unit. An ideal system that adopts such architecture is the human brain. The neural networks offers an insight into the in-memory process. Several attempts have been made to mimic the neural systems using nanoscale electronic devices, metal oxides, metal insulator metal structure, carbon nanotubes, and organic electronics. They were either speed limited or difficult to integrate. While photonics offers high speed, it is not trivial to store photos. It is not trivial to store photos. Non-volatile phase change materials offers desired electrical and optical characteristics. To realize such state, storage and neural networks. By choosing the desired phase of GST, one could control the synaptic weights in a neural network. By choosing the desired phase of GST, one could control the synaptic weights in a neural network. In the earlier works, sharp amorphous to crystalline transition was used to address two weights. Sharp amorphous to crystalline transition was used to address two weights. To address multiple weights, multiple patches of GST was used. In this work, for the first time, we demonstrate controlled crystallization of thermally evaporated GST to access multiple phases and its optical characteristics. The demonstration simplifies dynamic synaptic weights assignment with a single element manipulation. So here figure 1, XRD spectra of as deposited and annealed 200 degrees centigrade GST film 1A, a atomic force microscope image of 200 degrees centigrade annealed, that is the figure B, and C as deposited film is D, heating cycle of RT measured with different endpoint temperature. So this is the temperature versus resistance. Scanning electron microscope image of fabricated test device. So this is a ring resonator. So material characterization. Amorphous GST is deposited using the thermal evaporation technique on a substrate maintained at room temperature. The film was crystallized by annealing at 200 degrees centigrade and it was confirmed using X-ray diffraction, XRD, figure 1. The crystallized film shows, so amorphous GST is deposited using the thermal evaporation technique on a substrate maintained at temperature this. The film was crystallized by annealing at 200 degrees centigrade and it was confirmed using X-ray diffraction, this figure 1A. So figure 1A, so as deposited at 200 degrees centigrade. So as deposited annealed 200 degrees. So this is deposition and this is annealed one. So this is amorphous and this is crystalline structure. The crystalline structure is sharp and this is 2 theta versus intensity XRD spectra. Now the film was crystallized by annealing at 200 degrees centigrade and was confirmed using X-ray diffraction. The crystallized film shows FCC structure, phase centered cubic structure at 25.8 degree less than 111 and 42.36 degree less than 220 less than, and hexagonal structure at 28.6103 and 39.8106. Figure 1B and 1C show the surface roughness of the as deposited and crystalline film. So both are there. As deposited means amorphous. So figure B, B is a 20-degree annealed. This is crystalline. This is amorphous. 200-degree heating cycle of RT, temperature 200-degree, and D is what? Okay, the resistance is decreasing in all cases. So 200-degree centigrade blue one, cycle 9, cycle 1, cycle 2, cycle 3. Okay. We observe a surface roughness of 0.76 nanometer RMS and 1.34 nanometer RMS for as deposited and crystallized film respectively. So roughness in case of amorphous is 0.76 and in crystalline it is 1.34 nanometer. Unlike the sputter deposition process, we achieved a low roughness film, which is a characteristics of the evaporation process. The roughness increase post anneal due to crystal formation, which can be clearly observed in figure 1c. In 1c, roughness increases post anneal. Uh, due to low roughness film, which is a characteristic of evaporation process. Figure 1c. See, this is resistance. C figure. Yeah. This is okay. Roughness is more, here less. Evaporation method and annealed method. Thermal evaporation. Okay. Time dependent electrical resistance. RT measurement. Time dependent electrical resistance of 30 nanometer GST film on glass substrate shows a transition crystallization initiation at 130 degrees centigrade. We observe a 20 degree centigrade transition temperature range where different crystallization phases could be exploited. Time, okay, the glass shows that transition crystallization initiation at 130 degree. So at 130 degree, which is here, so just 130 degree, this one, 130 degree. Time-dependent electrical resistance of 30 nanometer GST film on glass substrate shows a transition crystallization initiation at 130 degree. We observe a 20 degree centigrade transition temperature range where different crystallization phase could be exploited. Figure 1D shows the temperature cycling where a controlled crystallization phase is achieved, resulting in a different material state. Using the transition state, one could explore the associated optical characteristics for photonic neural weights. Device fabrication and characterization. Optical characteristics of GST film are characterized using a silicon ring resonator. The ring resonator is patterned by etching 70 nanometer of silicon in 220 nanometer silicon device layer on top 2000 nanometer buried oxide layer. Patterning is done using electron beam lithography followed by reactive ion beam etching. On top of the device, 40 nanometer of silicon dioxide is deposited as a thin layer before GST deposition. So what is going on here? So 220 nanometer silicon is there. Then 70 nanometer etching. Top layer, this is called 2000 nanometer oxide. Patterning is done using electron beam lithography followed by reactive ion etching. On the top of the device, 40 nanometer of silicon dioxide is deposited. So here, further 40 nanometer of SiO2. So this is silicon. This is silicon dioxide. It deposited as a thin layer before GST deposition. So 40 nanometer, and after that GST. Using a lift off procedure, 30 nanometer thick and 5 micrometer long GST is deposited using thermal evaporation. So lift off 30 nanometer thick and 5 micrometer long. So this is a 30 nanometer. Following the deposition and lift off process, titanium platinum heaters are deposited. After that, heaters are deposited on top of GST patch. Figure 1 shows a scanning electron microscope image of a fabricated device. Heater, okay, ring. So this is a top view, electron microscope. Figure shows, okay. The optical response of fabricated device is characterized using tunable laser source 1510 to 1630 nanometer and an indium gallium arsenide photodetector. An increase in the heater power results in the phase transition and change in the optical constant of GST. With increasing heater power, the resonance shifts towards a longer wavelength while the extension reduces. Figure 3a. So this is the power, milliwatt, heater power 0, 50, 10, 150, 200. The resonance shifts towards a longer wavelength while the extension ratio reduces. So figure 3a shows the reduction in the extension ratio. But 0, but what are these different colors? Transition region showing a non-volatile multi-stage extension cycle, extension at various heater. This is cycle and this is heater. Where is heater? 40 to 200. Resonance wavelength cycling and resonance shift with heater power. Wavelength shift from 15 to total how much? This 16 to 18. 2 nanometer phase shift. The linear shifts in the resonance indicates the thermo-optic response of the device dominated by silicon, while the extension shows a clear phase transition because of the optical absorption. The multi-stage transition is measured by cycling the heater power and cooling down without full crystallization, as shown in figure 3. In summary, we have presented material, electrical, or optical characteristics of thermally evaporated GST film. For the first time, we demonstrated controlled crystallization schemes for application in a multi-weight neural network with a single phase change element. So thank you for attending this reading session.